have Anita Grover, who's an assistant professor in our own CS department today, giving a talk here. And he has his research interests are involved in efficient machine learning application or approaches with emphasis on deep generated models and sequential decision making. He is an affiliate faculty member at UCLA Institute of Environment and Sustainability, and his research has real-world applications in climate science. He has published over 40 research works in top venues, including Nature Impact Research, deployed in public production of major tech companies like Twitter and Instagram, and he has received numerous awards, including Best Paper Awards, 2 Best Paper Awards for graduates and fellowships, 4 industry faculty awards, a certificate doctoral realization award, and Samsung's AI Researcher of the Year award. He is on a postdoc at UC Berkeley. He has a PhD from Stanford and bachelor from IIT Delhi, all in computer science. So he's going to talk about generative decision making under uncertainty. Please welcome
Thanks, Arash, for that introduction. And today I'm going to talk about generative models, which are all the buzz today. It's a topic I've been working on for the last 8 years. And what I'll talk about today is how generative models actually also offers us a window into intelligence more broadly, particularly in the sphere of decision making. So to first give an overview of my larger research interests that I execute at my lab at UCLA, so I lead the Machine Intelligence Lab, and our mission is to design intelligent agents that can interact and reason with limited supervision for real-world scenarios. Now, this mission encompasses a wide variety of subdisciplines that intersect together in many novel ways. So I work a lot on unsupervised learning. This includes models that I'll talk about today, for example, generative models, as well as modern approaches based on self-supervised learning that enable us to learn at scale. I think about how these models interact, can help us with interactive intelligence, where agents have to make decisions in a lot of complex scenarios that require rational thinking. And finally, I think about how all of these models also have some applications in the real world, particularly in the sphere of climate science. So I could talk about all of these different areas, but really I feel the magic often happens when they intersect. And today's talk, we're going to see one such intersection where I'll talk about how deep unsupervised learning enables sequential decision making at very large scales. So many endeavors in everyday reasoning involves us to interact with multiple steps of reasoning. So if you think about science, it involves designing sequences of experiments. Engineering requires us to design sequences of prototypes, and society, as we have seen very well with ChatGPT, often involves humans having the need to have sequence of dialogues and interactions with each other. Now, for all these applications, there have been a lot of advancements, and particularly one framework which allows us to formalize them is that one of reinforcement learning. So if we look at some successes of reinforcement learning, indeed, in the last 10 years or so, we have seen some major breakthroughs. So many of you might have seen headlines about AI learning to master the game of Go. That success catapulted into many other spheres. So AI has been used for designing sequences of experiments for chemical synthesis. AI has been also used for designing very sophisticated chip floor plans for computer architecture. During my PhD, I also got a chance to collaborate with material scientists in using these decision-making paradigms for designing protocols for electric batteries. And in spite of a lot of these successes, we find that they are few and scattered, and there is a big gap in translating them broadly to a wider range of domains that we care about for science and engineering. And if we peek into these advancements, we find why that's the case. And the reason simply happens to be that a lot of these advancements have taken place in environments where we have a lot of restriction on the assumptions we can make. For example, many of these domains assume that the dynamics are known, the state spaces are fully observable, or we might just have a very nice data set to bootstrap our learning from. So with these restrictive assumptions, while they indeed might hold in one or more domains, they're also the bottleneck in terms of generalizing decision making at scale for much more broader set of applications that we care about. So on the other hand, we also are living in this age of generative models all around us. So we have seen advancements in language, and many of us also have seen demonstrations in speech and vision as well of how we can generate very high dimensional data with very flexible tasks for what should be generated. So this kind of generalization and flexibility that we have seen in generative models is in stark contrast with what we see with reinforcement learning, which has so far worked for very specific domains, making a lot of assumptions about those domains themselves. So what this talk is going to be about is it will help us think about whether there's a synthesis between these two worlds. So whether the flexibility and generalizability that we get with modern generative models also translate to large-scale sequential decision-making using offline data sets. So I'll cover a lot of different paradigms of sequential decision-making, roughly in increasing order of complexity, and starting from a very simple setup on reinforcement learning known as offline RL. So the setup here is that an agent observes a log sequence of interactions consisting of triplets of states, actions, and rewards pieced together in the form of trajectories. And given this log data set, the goal of the agent is to learn a policy, how it should interact so as to achieve good returns when it's deployed in the real world. Now, what's noticeably different from offline RL and conventional RL is that the agent is not allowed to interact with the real world. So just using a log data set, the agent's goal is to learn a policy that will act optimally in the real world. Now, what makes this even harder is that we make no assumptions about the policy that was used to collect this log data set itself. So these behavioral policies will generally be suboptimal, and the goal would be that from suboptimal data, can we actually learn a policy that exceeds the performance of these behavioral policies? So offline RL has had a lot of excitement around it because it's really a way to scale decision making to large data sets. And the dominant paradigm in past work is to think about offline RL in the context of what we know about online RL, especially involving the use of forward surrogates. So a forward surrogate, we should think of it as any function that maps states, actions to a function that we can then use for obtaining the optimal policy. One such example is the Q function. So the Q function, if we learn the optimal Q function, we can extract the optimal policy very simply by taking the argmax and finding the actions that maximize this Q function. Now, while this proposal works very well, it's just a two-step proposal. You take your offline data set, you learn a surrogate Q function, and the second step, you just do argmax via gradient ascent to find these actions which maximize your Q values. And this is actually the heart of a lot of successes in RL. For example, the DQN algorithm, which was used to play Go, was also based on these similar ideas of learning a forward surrogate. But there is a challenge, and that challenge is in the offline RL setup, when agent is not allowed to interact and gather more data set, this method fails drastically. So there has been prior work which shows that Q-learning style methods suffer from a distribution shift problem in the offline RL setup, which is to say that the state action distribution that these Q functions are learned on will be very different from the state action distributions that the optimal policy would visit. So in that case, because of this distribution shift, these Q values in practice for high dimensional environments turn out to be very overconfident at actions which are actually having really poor values, and very underconfident and giving low Q values to actions which would have been executed by the optimal policy. So this generalization does not work very well when it comes to offline RL. There have also been follow-up works trying to mitigate some of these difficulties by regularizing the Q function during training to be a bit more pessimistic when it's encountered states action pairs that it did not see during training. So the design of these conservative regularizers is a little bit more involved and complex, so I'll skip the details. But what I want this talk to motivate in this talk is a different paradigm, where instead of focusing on forward surrogates, we think about inverse surrogates and whether we can learn them efficiently in an offline RL setup. So what is an inverse surrogate? Well, to best understand inverse surrogate, it might be good to think of RL as a special case of black box optimization. There is some function f, which is a black box. We don't know what f is, except that we might have some evaluations of f. And our goal is to find the argmax of f, the argument that maximizes f, x star. Now, RL fits into this paradigm by simply thinking of f as the expected returns with some discounting gamma, and the policy which maximizes these expected returns is what we are looking for when we do black box optimization for RL. Now, if we look at this kind of formulation, it becomes clear that the forward function f could be one that maps action sequences to returns, and the inverse function f inverse is the one which does the opposite. It maps returns to action sequences. So we will do something similar. We will try to learn an inverse, and in particular, given some return and state sequences, we will try to see if we can learn a distribution over the action sequences which will achieve those returns. We'll see in a bit how we will do that in practice, but if we do this, the recipe becomes very simple for inverse surrogates. Step one being simply to learn the surrogate for this inverse map using our offline data set, and step two be to use conditioning of this inverse map at some target returns in order to learn an optimal policy. Okay, for example, if we want to get the optimal rollouts from this policy, all we have to do is condition this model on the expert returns or some really high value of returns if we don't know the expert returns themselves. In some cases, for example, if you're trying to play games, the expert returns simply might be 1 for victory or 0 for loss, so there it's easy to specify. In some other domains, we might have some domain knowledge of what those expert returns could be. So once we do this, we get an algorithm which can help us solve the offline RL problem. But there is one challenge. And the challenge is, as many of you might have thought, this inverse is very likely going to be a one-to-many map. So for any target return, there could be many possible action sequences that achieve that return. And in this scenario, when we're having a one-to-many map, we need an algorithm which learns a stochastic mapping from these returns onto our actions. And this is where we can bring in generative models. So generative models have excelled at learning very highly multimodal distributions, and they can be efficiently conditioned as well if needed, as we have seen in the case of many of these advancements in DALL-E, ChatGPT, and a lot of the other generative models that we see around us today. So what we proposed is decision transformers. So decision transformers is one of these autoregressive generative models, which learns a distribution over actions conditioned on the dynamic value of returns and the states that are encountered in a sequence. So essentially, this visualization shows how a decision transformer is parameterized. We have a transformer backbone, and as inputs, we feed in the returns that we care about and the state sequence. And in order that follows the causal time steps, we predict the actions one after the other. Let's go a bit more into the details of this model. So what we do first is to specify our input. We take our offline trajectories, and then we process them as a sequence of triplets, one after the other, indexed by their time steps. So a triplet consists of returns to go, which I'll define just in a bit, and the state and action at that time step. So the returns to go is essentially the sum of returns starting from a particular time step till the end of the episode. So the sum of rewards starting at that time step until the end of the episode. So that's what we have defined here. So it's in some sense a dynamic value of how much returns the agent still has to achieve so as to satisfy its initial target. As output, we will predict for each each prefix sequence what the action distribution should be for the current time step. So initially, we will have just as the full cumulative return as input along with the first state, and we'll have a distribution over the first action. For every subsequent time step, we will append the new states and the updated returns based on the rewards we achieved from the environment, as well as the actions that we had previously predicted for the previous time steps. So given this input-output format, we have specified an inverse model. And how we learn this inverse model is simply through supervised learning. If we have discrete actions, we use the corresponding supervised loss, for example, the softmax cross entropy. If we have continuous actions, it's going to be the mean square error. So there is no dynamic programming anywhere in the setup. It is simple supervised learning. And here is where we can actually benefit from the vast literature in supervised learning on how to stably specify expressive functional mappings through deep learning, how to optimize them through gradient-based methods, and also regularize them in other ways as and when needed. So all of those techniques now become available to us in the RL setup as well. Once we train such an inverse mapping, we can also use it for policy evaluation and think of policy evaluation as simply rolling out a generative model for multiple time steps. So we start with some initial state that we get from the environment and some desired returns, for example, the export returns. The transformer gives us the first action, which we append to our sequence along with the next state and the updated returns to go, and repeat this process till the end of the episode to get a full sequence of actions that will be executed by the agent. So training and testing is very simple. It works just like how you would train and test any autoregressive generative model. It's quite stable to train in practice, and I'll show some of those effects on the stability in my experiments as well. So now that we have this full pipeline, how well does this actually work? Now, our paper has a bunch of different experiments to better analyze the working of different transformers. I've handpicked a few of those results, which I think are most insightful. And many of them will try to get to the inner workings of why this paradigm, as I would argue, works better than using forward models. So first, some summary results. So we tested on many environments, and here I'm showing an aggregated performance. So in Atari, it consists of many environments for game playing, where you have images as your state spaces and your actions are discrete. In OpenAI Gym, you have many environments, again, which have the task is to do locomotion. And so it's a benchmark suit for continuous control, where you have both continuous states and continuous actions. And finally, Key2Door is a challenging environment which I'll describe in more detail in a few slides, but essentially it's one environment which really requires you to understand sparse rewards and long-term credit assignment. And what we find in these summary results is that if we compare different transformers with forward models, so in this case, we used conservative Q-learning as the benchmark forward model, which was state of the art at that time. And if we compare our model with CQL, we find that different transformers are very competitive and match or slightly exceed the performance on Atari and OpenAI Gym, but they are much, much better when it comes to environments which have sparse rewards. And this behavior cannot be obtained by other supervised learning paradigms for RL. For example, if you know about behavioral cloning, it's one of the most classic approaches to do RL via supervised learning, but those approaches are not what gets us this level of performance. You really need to think deeply about how to structure your sequences and how to use conditioning to get these benefits. So let's go a bit more deeper and unpack these results to understand what's going on. And before doing that, we should first maybe think of a broader question. What does it mean for a decision transformer style approach to generalize? So in the next few slides, we'll see a lot of plots which have this flavor where on the x-axis, we will plot the return that we use for conditioning at the first time step. And on the y-axis, we will look at what is the return that is actually achieved by the agent. Okay? And there are three possible scenarios that could have happened. So this is just an illustrative plot of those three scenarios. Now, in the first scenario, which is what I call the ideal scenario, what you feed in is what you get. So if you want a target return which exceeds this green line, which is the maximum return in your offline data, it's still okay. The model generalizes to higher returns and does achieve them very faithfully. But there's also other two scenarios which are probably more realistic here. And this second scenario is the one where we see unreliable generalization, in which case, for the maximum return the offline data, we have very little trajectories which have this data. So typically offline data will have a spread of trajectories with different returns, and around the maximum you have very little trajectories. And furthermore, the problem gets worse that if you start exceeding the maximum and going towards the expert level returns, then you have no data at all. So in this regime where you're trying to generalize to these high returns, the model could drastically start failing. So you condition on something very high, which is what you typically want, but the model starts actually giving really poor performance when subject to these out of distribution returns. Now, the third case is a middle ground. So this is what we call as reliable generalization, in which case conditioning near the maximum or beyond it preserves the performance and it or slightly exceeds what was the maximum return seen in the offline data. Okay. So now you might think this unreliable case is probably is not something we might see in practice, but actually a lot of the forward algorithms exactly suffer from this kind of problem, where anytime you go to a state action pair that's outside the distribution of your offline data, your Q values are not reliable at all, and they will generally give a policy which is much worse than what we would expect from the optimal policy. So what about decision transformers? In this landscape of generalization, where do they stand? And what we have seen in practice is that decision transformers are somewhere between reliable generalization and the idealized scenario, wherein here, for example, I'm showing 4 environments. The first two on the top row are from Atari, the bottom two are from the OpenAI Gym, and this for the same X and Y axis that we had previously. If we plot these returns, we see that beyond the maximum return in the offline data set, these models either show reliable behavior, as we can see for environments like Half Cheetah, Hopper, QBERT, or in some cases, they actually continue to exceed in the performance, depending on higher conditionings that we provide the model. So they do generalize pretty well, approaching close to idle behavior as well, as we see in Sequest. So this is very positive news for inverse models and decision transformers in particular, that they don't tend to suffer from a collapse in performance when subject to out of distribution inputs, unlike the forward models that are typically used in these cases. And one thing I want to emphasize is that these results did not do any, we didn't do any kind of explicit regularization to ensure these kinds of behaviors emerge. We didn't try to, whether it's in the loss or in the data set filtering, there was none of these tricks that we tried to apply to get these results. It was very naturally emerging when we did these experiments with this kind of model. So that makes us wonder why. Why is it that when we're subject to out of distribution inputs, do we see at least reliable generalization, if not the ideal case? And so we did try to do a little bit more analysis in ablating and actually weakening our model to find out what is it that causes this generalization in practice. And one explanation, it's not the complete picture, but at least it's an empirical insight that we found, is that there is a big role to play in the architecture itself. So what we did was we created this ablation baseline called decision transformers concat, which essentially concatenates the state and the return to go tokens instead of treating them as separate tokens. So you think of returns to go as just an extension of your state space. Now, if you do that, essentially when you're trying to learn the inverse function, you'll not have any kind of attention being computed in your transformer between these concatenated tokens, Whereas in our original scheme, we considered them as separate tokens, which allowed us to apply attention to across these different tokens at different time steps. Now, if we do that, this DT concatenation instead, we find that we start seeing this unreliable generalization emerge here in these plots, for example. So beyond a certain value that we saw in the offline data set, the performance starts crashing, and these models start suffering from the same kind of behaviors that we saw with the forward models. So there is more to be done here. This is just some insight that we have, but I'm sure from both theoretical and empirical perspectives, there's more to be understood about why this generalization happens and if there are alternate ways of achieving it even without attention. So another result that I wanted to highlight from this work was on using these models for long-term credit assignment. So if you remember the results from a few slides back, the one in kind of environments where decision transformers really shine a lot over other approaches was environment called key to door. And it's one environment where we have sparse rewards. So I'll quickly describe the setup. So in this environment, the agent operates in 3 sequential phases. In the first phase, you place the agent in a room with a key. In the second phase, the agent is transported to a room which is empty. There is no object out there. And the third phase is one where the agent ideally would want to use the key in phase 1 to open the door. Okay, so as you can see, phase 2 has no intrinsic value for an agent excelling at opening the door with the key, but it's put in to elongate the episode. And this is one of those scenarios which really causes catastrophic failures for a lot of RL methods. So in this kind of environment, you really have to do credit assignment over a very long time frame to understand that picking the key in phase 1 is what leads to a good reward at the last phase. The reward here is sparse, so only at the final time step you receive a reward if you reach the door and had picked up the key in phase 1. So here are some summary results first before we do a more qualitative analysis of this environment. So for different number of trajectories in our offline data set, we find that distant transformers achieves much better performance than conservative Q-learning or behavioral cloning. We tried to create a hybrid between distant transformers and behavioral cloning, which also works well for this kind of environment, but not the others, which is the percent BC base ablation baseline, and the random performance is too low, but just included here as a reference. So distant transformers work much better than conservative Q-learning and other supervised learning approaches based on behavioral cloning. So it's important to understand also if these performance can also be qualitatively assessed. So here we did a twist in which we took the same distant transformer on key to door and looked at, can it serve as a predictor of rewards? So in the original model, we use distant transformers as actors in which they are supposed to predict sequences of actions. And in this particular case, we thought, can we use the same model as a critic, in which case it will have to predict the probability of achieving a reward as the agent progresses through an episode. So what we see here in this figure is that on the x-axis, we have the 3 phases. So phase 1 is the one in which you have to pick the key. The second phase is the distractor phase where there's no object and the agent just has to hold on to the key. And the third phase is where the agent has to open the door with the key. And what we're seeing is that what happens to the predicted reward probability as the agent navigates through each of these 3 phases. So here are 3 scenarios. So let's look at the first scenario in blue, in which the agent does not pick up the key. So as we can see, as a function of time in phase 1, the probability of a reward keeps going down as it becomes harder and harder for the agent to pick up the key in the remaining time, and until it drops down very close to 0. And this does not change as we go to phase 2 and phase 3 because the damage has been done in phase 1. So the agent has learned that if you had not picked up the key in phase 1, then your final reward will be 0. Now, if you do pick up the key, there are 2 interesting scenarios. So let's look at the second scenario here in dark orange, where the agent does pick up the key, in which case the probability of getting the final reward rises slightly, and it stays constant in the distractor room because there's no other evidence to suggest that this probability should increase or decrease. And finally, in the last phase, when the agent starts approaching the door, it increases up to 1. So this is again consistent with the behavior we would expect from an intelligent agent which can do long-term credit assignment. The third scenario is also interesting, where phase 1 and 2 operate just as before. In the green and the brown probabilities are roughly the same. But if the agent had not reached the door, even the predicted reward probability goes down to 0. So all of these go on to say that these models are not just great actors as we see in the previous results, but this environment also illustrates that they are very good critics, and that's especially important when you have sparse rewards and you need to do long-term credit assignment. Okay, so this was the bulk of the talk that I wanted to discuss about distant transformers. But now I also want to show how this framework actually extends to other paradigms in decision making. And this is an analogy to be also learned in trying to map this paradigm to generative models and how they are applied to customized domains today. So if you look at any generative model, typically there are 2 phases. The first phase is called the pre-training phase, where you would try to learn a generative model on some large unlabeled data set, such as the text you might have scraped from the internet. The second phase is where you think about fine-tuning this model onto a domain that you actually care about. So if you care about healthcare, you might try to gather data from healthcare to fine tune this model. If you care about if you care about climate domains, you might want to optimize these models on those data from those domains, and so on and forth. Now, in all of these phases, there is a bulk of the work happens in phase one, where you have a big data set, and you want phase to be generally more efficient and require less data. We can ask this question again for RL: what do these phases look like? And the answer here is that we can actually think of whatever we discussed so far in offline RL as our first phase, where the agent is not allowed to interact, and the phase two, where the agent tries to improve upon the policy it learned in the offline RL phase through interactions with the environment and getting more data that helps it specialize to its domain and reward function. Okay, so that's how one perspective to think about these analogies, and that's the perspective which we also tried in our follow-up work, where we thought about, can we take our pre-trained decision transformers? They are not always optimal, but can they approach optimality if we then fine-tune them and explore to get more data and improve their performance? So in online decision transformers, the key technical question to be asked is, how do we allow this model to explore and get data that helps improve its performance? So now exploration has a very rich history in artificial intelligence. There are many, many different criteria that people have explored for exploration. And in this case, we borrowed inspiration from the principle of maximum entropy, which has worked very well for previous active critic methods. And we extended that method for architectures like decision transformer, which work on sequences. So essentially, the framework we used here was to minimize some cost function, for example, the mean squared error or any supervised learning objective that we use for decision transformers, subject to some lower bound on this sequential entropy of our policy. So what has changed here are two things. Now, in contrast to regular RL methods, where J is typically the negated expected returns, in our case, J is going to be a supervised learning loss because we're using inverse models. That's chain number one. Chain number two is we have also slightly altered our definition of entropy. So typically entropy in online RL methods is computed based on individual transitions. So you want every transition to have an action probability from a distribution which has some lower bound on the entropy. But now we are working at sequences. So we define entropy which operates at the level of sequences. So for individual time steps, the policy action distribution can be very deterministic. It might not have too much entropy, but on an average, it should have relatively high entropy, at least exceeding the lower bound beta. How do we solve this kind of optimization problem? Well, here we borrow techniques from past works in which we construct a Lagrangian with the primal and dual variables as theta and lambda, and then we conduct an alternating optimization algorithm to optimize this policy. So this is how we define an objective for exploration. But one other important criteria here is, what do we condition on? For any inverse approach, the conditioning is a very important part of the overall algorithm. And even when we have to gather more data, we have to specify how we condition this model on. So in traditional Maxent RL methods, you just have a single policy, so there's no conditioning, things are fine. But in the case of online decision transformer, you have to think about how the conditioning itself will play a role in exploration and exploitation. So we tried many schemes, but the scheme that worked best is very simple and it follows Occam's razor. So we conditioned our policy on the export returns. So we tend towards exploitation, but our policy has not been trained it's not optimal already. So the returns that we actually observe will inherently have some noise in the actions that are taken and will return in something which is suboptimal. Now, this might create a bias as well, which is that what we are conditioning on is not what we are getting. So when we have to include this new data in our offline data set, we need to make sure that the returns are correctly fixed. They're not set to the returns that we wanted. Rather, it makes sense to have the returns that were actually achieved. So this is what we call as hindsight return relabeling, where initially we had some desired set of returns to go, but we observed something different. And in hindsight, we relabel those returns before appending our trajectory onto our offline data set and expanding it for better learning. So hindsight relabeling was very critical. So here in these plots, what I'm seeing on the x-axis is the progression into the agent gathering additional online samples. On the y-axis is normalized returns, so higher is better. And for a range of different RTGs, we see that if we did hindsight return relabeling, we were able to achieve optimal performance of 100 when normalized. Whereas if we had not done this hindsight return relabeling, we would have quickly saturated onto a performance not much greater than the offline performance itself. So this summarizes the overall algorithm. You first pre-train your decision transformer on some offline data set, and then you roll out a trajectory on the optimal returns, conditioned on the optimal returns. You observe some sequence of actions which may have a different set of rewards that do not add up to what you had conditioned on. So you apply some hindsight return relabeling to fix that. You append these trajectories to your offline data set and repeat by updating the policy and gathering additional data. So some summary results. So I'll just show the aggregated performances here. So on the first column, we are seeing different environments we tested on. The second column was the offline performance. The third column what happens when we update these offline performance with online fine-tuning, as I just described. The fourth column is the delta between the two. And the last three columns repeat this exercise for a Q-learning algorithm, which was state-of-the-art at the time we developed this algorithm. And the summary is that our model after fine-tuning is better or comparable to, again, Q-learning algorithms which use a lot of regularization, and the aggregate performance after pre-training and fine-tuning is roughly the same. What's really nice is also that actually, if you see our architecture, there has been a bigger jump from pre-training to fine-tuning. So the delta between the pre-training and fine-tuning happens to be much better for the online decision transformer as opposed to the Q-learning style of algorithms. And this is something not to be taken for granted, because unlike other domains in perception, in RL, it has again been shown that there is a big possibility of negative transfer as we go from a pre-trained model and gather additional data through fine-tuning. But so the delta being positive by a bigger magnitude is a good sign to use these models, not just for large-scale pre-training, but also fine-tuning them to more specialized domains. So since these works, there have been a lot of follow-ups from many research groups trying to extend these methods. One such work which got a lot of attention from DeepMind was a generalist agent, where they designed a single agent that can play games, that can write captions, that can generate images, and do a lot of these different tasks using a single architecture, which is what they call as generalist. And the heart of enabling a lot of these different tasks, many of which involve taking actions, was to adopt an approach like decision transformers and using that as the base and combining a lot of different data sets from many different domains in order to enable this kind of generality. So the very last thing I wanted to talk about was to shift gears to a different paradigm of decision making, but show how the methods I presented today in using inverse models actually apply very well even to those other domains. So far we have been talking about a specific kind of black box optimization, which is stateful. So which is very useful, for instance, in applications in robotics. But there's also decision making that happens over objectives which are stateless, where you simply have to, for example, select a sequence of experiments, or you have recommended systems where you might want to recommend a sequence of movies. And all these cases, often the way a problem is formalized is stateless. But turns out these approaches, both all of the theory that I discussed for the previous works and the empirical insights do carry over here as well. So again, if you just look at forward models, these models do not generalize very well for stateless settings. And this has very good connections with adversarial examples as well, if you're interested. I won't go into those details, but the interesting bit is, again, if you applied an inverse modeling approach where you go from regrets to actions, you find that inverse modeling approaches tend to work much better in practice. So this was another overall pipeline we designed for stateless black box optimization. And a key important step here was this phase 1 that I described here, in which we had to take a data set of points and convert it to a data set of sequences. So if we have to use transformers, we need sequences which are apparent when you have stateful settings. But in stateless settings, there is no natural notion of sequences from an offline data set. So we designed a heuristic based on sorting, which is very natural. You simply sample a random set of points and sort them in ascending order of their actual regrets, and then, in the actual order of their function values. And that gives you a sequence which you can then feed into an autoregressive transformer to imitate. So with this simple heuristic appended to our traditional pipeline, we were able to learn an inverse model even for stateless settings. And in comparisons with, it works really good. So here, the columns are environments from a wide range of domains. So these are domains from biology, these are domains from mechanical design, and this is a domain in hyperparameter optimization for machine learning. We compare our approach against a wealth of different methods from evolutionary sciences, from Bayesian optimization, as well as some newer approaches based on GANs. We find that on average, our model does pretty well. And it has the mean performance and mean rank are very close to the best, if not the best, for all these environments. So that's essentially what I wanted to talk about in terms of the different paradigms of decision making. And one key takeaway that we can take from all of these discussions is that deep generative models are natural fits for learning inverse models for sequential decision making. And in many scenarios where we especially have large offline data sets for which quality may not be guaranteed, that could be a very powerful way to learn mappings which generalize well to different settings at test time. And the larger hope from this exercise is that now that we're using the same kinds of architectures and losses for control as we have been seeing for perception from ChatGPT, DALL-E, and whatnot, there is a big hope for integrating them in one single architecture. So a lot of my ongoing work, as well as work being done by the community, is trying to make this paradigm more generalizable with real-world desiderata. So we are looking at how multimodal data can make this offline data sets have more coverage. We're looking at multi-constraint settings, because often decision making is subject to constraints such as safety. And then we're also thinking about how we can design algorithms which involve not just a single agent making actions, but also different agents interacting with each other to achieve a certain goal. So we have an iClear paper which has some of these ideas, and for a lot of other ideas, we are still having a lot of work in progress. So with that, I'd like to thank all my students and collaborators who did all this hard work. Thank you.
Thank you very much. Any questions? Yes.
Hi, thank you for the presentation. Very interesting. I have a question for using transformer. Since it's an offline algorithm, so how much does the performance of the algorithm depend on the quality of the data? So like how are the trajectories on that? So I can see from the basic problem, obviously performance is really good as compared to the other algorithms. So is it because the training data is better or is from the performance or something?
Yes. So for the key-to-door environment, the data set being used for all algorithms is the same. But in general, offline RL strongly depends on what is the quality of the offline data. So in our paper, we actually tested with data sets of varying quality. So previous work has designed a way in which we can judge the quality of a data set in terms of what distribution of returns we see in it. And indeed, the better the quality gets, easier it gets for not just decision transformers, but for all other approaches to improve upon it. So a lot of the existing benchmarks for offline RL, which consisted of a large fraction of expert trajectories, are essentially not very useful now for comparison. So even in the ongoing projects we have, we focus more on the environments where the quality of the data is pretty low. And that can be measured by looking at distributions of returns.
Yeah, great talk. Kind of related question. I guess, like, did you find that the variance of performance was better for the decision transformer method than other methods? As in, like, when data was shifted, did you see that there was less of a change in performance compared to other methods?
Yes, so we saw it in two ways. One is exactly what you mentioned, that the variance is low if you just change the randomization of the entire algorithm. We also see it in a way that there's less sensitivity to hyperparameters. And that's partly related to how I define reliable generalization, that even if you think of the returns to go as a hyperparameter at test time, once you exceed the threshold that you saw in your offline data set, there is little degradation or change once you exceed it. So even hyperparameter sensitivity is quite low for these kinds of models as opposed to other RL algorithms.